Today I want to tell you a bit about what it means to build machine learning applications for sort of safety critical use cases where, it's really about making sure that there's no failure in the application. We believe that with autonomous flight, you can really solve some of the world's largest traffic problems. So hands up for anyone that has seen any of these on screen here. Who has seen some of these pictures? Very cool. I guess, even if you're not familiar with these aircraft, you should have seen the Jetsons. So we call these aircraft electrical vertical takeoff and landing aircraft. So they are pretty cool. They take off vertically and then they transcend into forward flight. And then you can go to your destination and they will touch down again. Now, from the Lilium to the Volocopter, there are over 100 companies in the world now that are really in an interesting race to try to bring these aircraft to market. As I mentioned, these are fully electric. And part of the reason why these are now becoming a reality is because batteries have become so much better over the last decades, while at the same time becoming much cheaper. And so that is great because electric propulsion systems are generally much simpler, and from an engineering standpoint, simpler is great because we have better introspection capabilities. We can understand the system much better, and eventually it will be much safer. At the same time, these aircraft have much smaller propulsion systems. So you see the Volocopter, if you've seen some pictures, has really these like small fans. So they're really suitable for urban transport where you have these flying maybe 150, 200 meters over your heads, where in situations where you don't want to have a big traditional helicopter flying and making all the noise that it makes. Now, for any of these to become wildly successful, they need to be operated at scale. And so the picture we really have in mind, if any of you have seen like the Fifth Element, where these aircraft are cruising around and bringing you to your favorite destination, there is already a shortage of pilots. So if you have that picture in your mind, we clearly need more pilots to fulfill the task. But at the same time, the task at hand becomes much more demanding because suddenly you have aircraft flying around everywhere, and you need sort of 360 situational awareness, and you need to be able to look into all directions to make sure you don't fly into anything. Also, again, we are operating in confined spaces, so you might be flying through buildings or in between buildings, I should say. So really, the task becomes really demanding. There's a completely different perspective you can take at this. So the Volocopter, or most of these, they have sort of two to four seats. So if you now have a two-seater aircraft, and you can you have a pilot there, that's 50% of your capacity. So the cost per passenger is extremely high compared to what you have in a Boeing 747 or something like that. For us, if we look at any of these problems and put them all together, the solution becomes very clear. And we need to enable these aircraft to operate successfully, we need to take the human out of the control loop. And this is sort of the slogan that pilots have to become AI in the long term. So this brings us to really what we are building. We want to build a fully autonomous autopilot for these aircraft. So fully autonomous means there's no pilot on board. And we want to show that we can clearly outperform the human on each and every dimension that involves flight. So we started this company about 3 years ago, and we went back to the drawing board, and the natural question we ask is, if any of you want to become pilots these days, what is it that you have to do? So what is the exam sort of that you have to take to become or get your pilot license? There's a theory exam, which is pretty simple for a computer because it can just remember everything. But then there's a practical exam. And what we want to show is that for all these requirements that humans have to sort of pass to become pilots, we can, be at least as good as what humans can do. So if anyone has ever looked at aviation, we talk about this later, but it's super controlled and very tightly integrated environment. So we want to make sure that we build this system with as little changes to the existing components as possible. And we look a bit at what that means throughout this talk. With as few dependencies as possible. So, if any of you have gone flying in general aviation, meaning anything that's not commercial aviation, you went flying with your friends or you went on a tour, people actually have to give you a weight. So how heavy you are, so they can calculate sort of the takeoff weight and how much fuel they need and so on. So we need to come up with a simple design that allows us to not rely on 26 sensors that we can put on the aircraft. And again, we will see what this means in more detail. We want to have as few dependencies as possible. And then, which brings us sort of to the meat of this talk today is we want to build this autopilot in such a way that, we are within the rules of certification. Now, this is what the system actually looks like. I hope also the people in the back can see some of this. You see there are cameras on different airframes here. We essentially, this is what the system boils down to. It's a range of cameras around the airframe, and the system is actually performed in such a way that it can perform all the emergency tasks. So, if anything goes wrong, you want to land, for example, with a single camera. Now, for full functionality of the autopilot and redundancy, we are probably looking at a dozen cameras, so 8 to 12. And as you can see here, the system is relatively airframe agnostic. And the reason for that is that we are focusing really on the high-level perception and sort of decision-making capabilities of the autopilot. So we have a pretty beautiful drone, the Wingcopter, that we are regularly testing with in the top left here. We have an R66 helicopter where you have our camera mounted to the side of the frame. We have the Volocopter that we've conducted extensive testing with, where we have a 3-camera rig here for situational awareness and also detecting other things that are in the air. And then here we have a general aviation Cessna-like aircraft where one camera is mounted underneath the wing, and then we have a forward-facing one just here. So also what I should mention is we are in a first step looking at building an autopilot for VFR operations. So this is visual flight rules, and it pretty much means that the weather conditions, for example, need to be good enough so that you can fly visually. So a good example is that you need to be able, as a human, to keep a reference point to the ground while you're flying. So, everything you're seeing here is in the context of these conditions. Obviously, if we talk about snowstorms and things like that, then we are taking that into account, but not in this talk today. Now, this is what the system actually sees from the aircraft. So this is our visual landing guidance system. It's a fixed-wing aircraft that's trying to land on this runway over there, and we have sort of an image object detection system here, where we are recognizing the outline of the runway, and at the same time we are providing what is classically known as an instrument landing system. So the pilots in existing cockpits these days, they have the exact same instrument here. I can just play it again so people can see. This is the instrument landing system that traditional aircraft also have. And what pilots are doing here is they are navigating or sort of positioning themselves relative to the runway so they know how to fly to touchdown in the middle of the runway. Now, what I should mention is here, this is purely vision. There's no GPS involved. So all the predictions that you see is the prototype that I put together for this talk last week. So everything you see here is first of all completely unfiltered. So it's the raw output of the system. The system only sees what you also see here. There's no GPS, nothing like that involved here. So looking at these examples, we're getting closer to what I really want to talk to you guys about. Existing aviation is extremely secure. We had an interesting conversation in the office the other day around are you actually less likely to be part of an incident while you're sitting on the plane compared to on the ground? And it's an interesting discussion to have because, purely the fact that you're buckled up and can't, sort of fall over in your household or, do any of the other things that commonly happen to people, it sort of shows that, it is the safest mode of transport. And that's for good reason, because everything that you build for aviation is extremely regulated and tightly controlled. So at the same time now, we are looking at all of these examples, including the ones that I've shown you, where we think that there will not be autonomy without introducing AI to existing aviation. And AI is a buzzword here, but we are talking about fundamental neural network-based techniques that we will talk about later. So there will be no autonomy without AI, we are convinced. And at the same time, the systems that we are building today, they can already help make existing aviation safer. So again, if any of you has ever been in a general aviation aircraft, having 360 sort of surround view is just not available to the human pilot. So for us to have a system that we can put on existing aircraft and make it look into all directions, that already is a step towards what we want to do, but also even today makes aviation safer. So again, aviation is extremely safe, but now we are introducing, what the general public refers to as AI to aviation, and more specifically, we are building the first applications that are based on neural networks, and we cannot compromise any of that safety. So let's take a look at how the system actually looks like that I've just shown to you. So this is our visual landing guidance system. I believe some of the text is a bit small, but don't worry about it. I'll talk you through. So I mentioned there's no GPS whatsoever, and here's a breakdown of what this looks like. It is a simplification, but the essential bits are here. So we have an RGB camera that gives us the images that I mentioned from around the aircraft. We have a pre-processing module that takes these images. It does a bunch of things. Part of it is downscaling the image, contrast enhancement, standardization. These are all very standard things we do in sort of standard machine learning pipelines too. And then we have our convolutional neural network, which takes in a single image and it outputs a prediction for that. The important bit here is that it takes a single image in, so we don't have any time dependency between frames. So all this network ever sees is single frames. And then we have a post-processing component where we can now take into account time dependencies, and we can do a lot of work on reducing false positives, false negatives, and so on. Now, this is extremely good to have this sort of overview, believe it or not. The reason for this is, again, we are introducing completely new techniques to an industry that is, for good reasons, I really mean that, stuck in the 90s. So when they hear AI, they sort of envision the monsters coming out and, doing all sorts of harm. Again, for good reasons, but it really helps to simplify this down and also emphasize that the only machine learning aspect or the only piece of AI that you have is here. And the rest is classical software that we know very well how to verify and also certify. So when I prepared this talk, I thought it would be a good idea to give people an insight into some of the challenges that we have building such a system. But obviously, I'm sure many of you are also involved in building machine learning systems all over the place outside of aviation in very different fields. So I wanted to walk you through a very common machine learning pipeline that shouldn't be anything new on this slide for you guys, but really look at what can go wrong in each of these phases from a safety critical standpoint. And I think this is really interesting to think about when if you are ever in a position to build something where what I call 80% machine learning is not enough, where you need to come up with more robust guarantees on how your system performs. Examples for that are, the medical industry. I've had interesting conversation about genomics earlier today. Aviation, obviously, autonomous driving. All of these are examples where, everything I'm mentioning here is extremely relevant. So let's look at data collection first. We go out there, we mount our cameras on the frame, and we fly around. As you will see later, my example is based on Switzerland because that's where we are based. But what can go wrong here? So we can have very blunt collection errors. We've had examples where the flight test team goes out and they sort of collect all sorts of imagery, and they come back and suddenly you have 30% pixel loss. So for some reason we weren't able to retrieve all the data from the cameras, and such corrupted data is not useful and can introduce all sorts of artifacts when we build a machine learning system. This is pretty obvious. Now, data biases is a more interesting one. So, we, as I mentioned now many times, we go flying quite a lot, and pilots tend to sort of fly in the same area or do the same maneuvers or do their kind of thing. So, we need to be very well aware that whatever data collection strategy we have, we can at least quantify the biases in the data and ideally remove them. Data is not traceable, so I think it's a very good thing that the machine learning community talks more about reproducibility of experiments, purely for academic purposes. There are all sorts of nice frameworks coming up that help you achieve this. We need to be able to have a model that we want to certify and put in production, and we need to exactly know which data samples were used to train, validate, and test this model. And this means it goes all the way back to the beginning of the pipeline, where we have sort of collection records of who went flying, what sort of cameras do we have, and which day, and everything. So we need to be able to completely reproduce where this data is coming from. And then the last one, I guess, is more trivial, but obviously something to keep in mind. We do a lot of data annotation. Data annotation is a tricky thing. We've had to learn a lot over the last 3 years. There was an example. I had a conversation with a colleague just 2 days ago, and we talked how we can mitigate annotation errors. And the obvious answer is, well, you have 5 people annotate the same image, and then you have an exponentially decaying error rate the more people you add. He mentioned, well, I worked on a project, and there were 19 annotators that annotated every single sample, but it was still wrong. And so then people started scratching their heads and said, well, what's going on here? And they realized, well, the requirements that each of these annotators received were just wrong. So something to keep in mind. Then obviously annotation errors, again, is the more obvious one. The interesting one is annotation biases. Now, if you look at sort of the annotation companies out there, they look a lot at, so they obviously, in our case, look at images. And keep in mind, they're all looking at these images most likely through the same screen. Not the identical screen, but they all have the same screen. So what if that screen has an artifact that makes them misannotate some of these images? I'm pretty sure we can find an example if we all annotated images now where we just all get it wrong because we think it's right, but it's not. So there are very subtle biases in there and very subtle risks that can then obviously translate into risks for your machine learning model. So at the core of the pipeline, we can obviously have an incorrect training process, or learning process as I call it here. Later on in the second half of my talk, I want to touch a bit on what it means for a data set to be representative, because that's something that's crucial to sort of everything we are doing. Then I'm sure many of you have heard of the bias variance trade-off. So even if we cannot avoid that, then we should at least be able to measure that and know how our model is performing. I mentioned reproducibility, and here again the more subtle one, which most people think is boring, but it's really crucial, is the common mode failures. So we tend to spin up our Google Cloud or Amazon instances. Then you have some Kubernetes job that just multiplies it over all the instances. Chances are you train all of this on the same hardware. So what if, for whatever reason, that hardware introduces some flaws into your model? The same goes for the popular machine learning frameworks out there. I wonder if any of you has ever used 2 frameworks to train the same model. Probably not, because it's very cumbersome. But these are things we all need to think about, because what if one of the, I'm deliberately not mentioning a name, but what if one of these frameworks have some form of bug that leads to erroneous behavior in the model that we produce. Then evaluation. The key really to keep in mind from here, as we will revisit it later in the talk, is that the generalization or any claims we make about generalization, so how our model performs during operation, is quite obviously done from our held out data sets. Now, we should really think about for a minute how much of our own subjective definition goes into that. And then at the same time, how subjective our assessment of generalization performance is. There's a lot of research around edge cases, and how do we expose our model during training to edge cases, and also very unlikely events that we see very rarely. Everything very important. And then here are, I think, a lot of sort of well-known terms. I have had lots of conversations around adversarial attacks. So some people think they are, a very nice research type of problem, but they will never appear in the real world or in real operation. Well, the opinions divide, but that doesn't matter, because we still need to be able to show, for example, that our model is robust to local variations in the input, which is what I also want to talk about. And then, the important one here is model behavior is not explainable. So if we talk again about authorities, about regulations, once there is an accident, people need to understand what happened. So this is why, from the first time we walked into the authorities' offices, they said, well, can you sort of retroactively explain what happened? That's also a very important one, which I won't touch on in this talk further, but something important to keep in mind. Now, going back to our pipeline, again, the key thing is really that in aviation, and really, it's actually nothing specific to aviation, but becomes even more important if you build safety-critical machine learning models, is that all our assessment of how the model will perform in operation is done during what we call design phase. And then, we will only get a chance to actually put our model into operation if we can convince people that it performs well enough during operation. So that's sort of a chicken and egg problem. And I want to spend the remainder of this talk giving you an insight in some of the work that we are doing to come up with guarantees on how we will perform during operation, and then also talk about robustness properties of the model. So, in other words, how do we establish operational performance before operation? Now, a good place to start is to probably define a couple of error metrics. So, we have our in-sample error, which is an error metric we can compute over the data sets that we use in the office that we have available during the design phase. And then we have the, what I often like to refer to as the hypothetical out-of-sample error. Not sure actually if hypothetical is the correct word, but the point here is that we do not have direct access to it because we just don't put it into operation. And then I'm pretty sure what many of you have observed is what we see at the bottom here. So then you do your evaluation and you see the model performs really well on the training set, a bit worse on the validation set. Then you think about sort of overfitting, underfitting, and whatever goes in there. It's better than on the test set, and then what we expect is that in operation, it actually performs the worst out of these terms that we have here. So this is not really useful to us because I'm trying to sort of come up with guarantees for performance in operation. So what I want to do, actually, I want to take this and not say that the out-of-sample error is the worst out of all of them. What I want to do is I want to show that the inequalities are as tight as possible so that these errors are as close as possible to each other without putting it into operation. Now, what we see here is, and this is what we should probably look at next, is that to compute the out-of-sample error, we sample from an input space, which I here refer to as X. It's actually an input probability space. It's probably worth looking at what that means, because that will then give us a way to compute that error and, again, know how the model will perform an operation. So I'm coming up with an example here. This is one of the airports where we fly pretty regularly. It's about 40 minutes away from our office. And for the sake of this argumentation, I want to have my input space be all the 512 by 512 RGB images that I can possibly record over Switzerland. So the way to think about it is we have infinite resources, and we can fly over Switzerland as much as we want and collect the data that's relevant to my application. So in this case that I showed earlier, I can fly over all the runways in Switzerland. I can do this every day and collect all the data that I can possibly ever collect. Now, if we think about this for a bit, we realize it's pretty easy to talk about this. I'm sure that I just mentioned, or described what our input space looks like. Everyone has sort of a picture, but it's very hard to describe this mathematically. So what is this space? We know for sure it's very high dimensional, very complex, very large. What is this space? And how do we now, come up with guarantees over this space if it's so hard to describe it mathematically? So going back to, statistical learning theory that I'm sure many of you have heard, and something that brings us ultimately to things like VC dimension, we actually, get something very nice that has been proposed for the first time, decades ago. And that says that for a class or type of models and for a training data set size, so we know how large our training set is, and an arbitrarily small failure probability. So the failure probability is here my guarantee that, the guarantee that I want to have for my model and operation. I want to be sure it does not fail more than this probability. And an arbitrarily small interval around that training error or the failure probability, I can actually guarantee that my test error is contained in that interval. Now here, the terminology is slightly changed, more sort of along the original statement, but really what we are talking about here is my operational error, so something that I don't have access to. Now there's a big if, as some of you may know. So the if is that the distribution of the training data is the same as that of the inference data, or as the data that I will see during operation. Now, I also said that, again, it's hard to actually look at that distribution or describe that distribution that we see in practice mathematically. So what can we do about this? So it's always a good idea to reduce complexity when you don't know what to do. And so we perform dimensionality reduction of this original space here, where we introduce what we call explicit operating parameters. So this is still in the context of our landing example. If you're flying towards a runway, there are a couple of sort of defining factors. The angle of approach, so how steep you are approaching towards the airport, the time of the day, which includes all things like sunlight, illumination, and so on. And then the speed, for example. How fast are we approaching that runway? Now, you can then illustrate that for this specific example as a nice 3D plot. This is actually one of our data sets that you see here. And then, if I now think back to what I want to do, I want to show that the distribution of the training data is the same of that of the inference data. So having these explicit operating parameters, the first thing I want to do is that I show the data sets that I have in my office that I use to train, validate, and test the model before operation are independently distributed in that operating space here. Now, some of you might say, well, but what does this give you? There are some pretty big assumptions you take here. And you're absolutely right. So that's actually not enough. But it still gives us a great way, first of all, to reason about that input space and communicate to authorities and regulators, and somehow put a more rigorous description of that space. But to come back to our guarantees, what we want to again do is we want to show that we have tight bounds for our inequality at the bottom here. We want to not only show that our data sets are independently distributed in these operating parameters, but at the same time, they're independently sampled from our input space, or input probability space. And at the same time, they also need to be independent from each other. So now, still the question is, how do we do that? And what we are proposing as a way to approach that is that you actually build an input distribution discriminator. So a sort of proxy that tells you, is the sequence of images that I'm currently seeing coming from my input space? And what we require here is that it outputs a number between 0 and 1 for a sequence of images, depending on whether you think it comes from that distribution or whether or not you think, or whether you think it doesn't come from that distribution. Now, we can then provide this as part of our machine learning model. It will also run off on the data that we receive during operation. And whenever this value drops, we know we do not have any guarantees on our performance anymore. And it might not be a good idea to actually listen to what the system is saying in more intuitive words. So what this, from a practical standpoint, means is that when you go to the authorities or to anyone you want to convince of your model, you really provide the model itself and then also this input distribution discriminator. Now, I can sort of, if I wanted to, some people would say, well, but you can cheat and you can just always make this guy output 1. So what we also require is people to provide a data set that's out of distribution to verify that my discriminator will output low values for that. And the nice property of this is that this is a very simple data set to collect. So now I can fly in Switzerland, and then I can hop over to France or to Austria, and I can collect data, and I can very easily label that as being out of distribution. To give an illustrative example. If we go along other dimensions, I can fly at night and then label that as out of distribution data too, because we only intend to fly during the day. And then, as long as our input distribution discriminator outputs a value that's close to 1, we actually have tight bounds here. Now, this is all nice, but there's a very big concern that we get from people that want to use specifically deep neural networks in safety critical applications. And they say, well, you can give me guarantees, but what if your model does something funky in between these points that you provide here? So how do we deal with this? The question is, how do we ensure that our model is robust to input variations? There are all sorts of things that you've seen out there, adversarial examples, small geometric transformations that we need to be robust to. And what we see here is actually an interesting experiment that we've done. So this is, we are looking at an intermediary layer of one of our neural networks. And I push the original input through the network, and I record that intermediary feature map of that neural network. Now what I do is I make a perturbation to that input. I also push that through the network, and I record how much of a change there is to this intermediary feature map. For a normally trained model, we can see that, it changes quite a lot. It's not very robust to any input, any sort of transformations in the input. Then there's the thing that people know very well these days is adversarial training. So what we do is we feed in some adversarial examples during training, and we can actually see it gets a bit better. So we still have quite some amplitude here, but the mean values are significantly lower than before for most of the filters down here. Now, adversarial training is nice, and certainly a technique to make your model more robust. But really the problem still with adversarial learning or adversarial training is that you're somehow still hoping for the best. So, I do this during training, and then I just hope that, during operation it's robust. So, we need to be a bit stricter on that. And how much time do we have left?
6 minutes.
Oh, great. Including the Q&A, or?
Including the Q&A.
Okay, that's good. We're almost done. So, we're extending work here that was proposed by the guys at DeepMind in 2018 called interval bound propagation. So we are, coming up with a way to robustly verify, provably verify that our model is robust to input variations. And I won't go into too much detail. If you're interested, it's a great paper that sort of gives you the initial findings there. But intuitively, what we are doing is we are making geometric transformations to our runway example. So for example, I would change the viewpoint slightly when I approach the runway. And then instead of passing a single point through the network, I pass this entire volume through the network. And then what I can do is check at the output layer that if there's no single prediction inside my ball that has the wrong class, then I have proven that my model is actually robust or provably robust to input variations. Now, fascinating topic. We do quite a lot of work on here, specifically because you end up with a pretty big, optimization that you want to perform here. And there's one thing here that, as we've heard in previous talks today, that there are elements in the neural networks that make the inner representations that you get non-convex. So what we do is we come up with an outer approximation to our non-convexities to be able to propagate this as a convex, what we call polytope, and then optimize nicely over it. The problem of this approximation is that as you make more changes to the input, the bounds that you get become very loose, and as you take it to extremes, actually become kind of meaningless. So what we have to do, and where we are working on, is to actually come up with better approximations going closer to what people have done a couple of years ago, which is exact propagation of these volumes through the network. Now, exact propagations are, like SAT solvers or in that direction are extremely computationally intensive. So what we are trying to do is to find the middle ground between, the convex relaxation techniques that we have these days and what we consider to be exact propagation. If you do that, now we are looking at the same model here, you see that we've actually become a lot more robust. And this is a nice thing because I can now come up with sort of a threshold here, and I understand how much variation I can make to my input to be able to have very little change in this intermediary representation, and then also in the output. Now, the use case that I've mentioned and where we are specifically using this and working on is, again, our runway detection system, just like all of our other systems for the final autopilot. And so this is an illustration of where we find bounds for brightness in the images, for example, rotations that we see there, and also translations in the image to show that we can find sort of these extreme points, and we can prove that everything in between is actually robust. Now, unfortunately, I only have 45 minutes to talk about this. We are going into much more detail of all of this with EASA right now, which regulates all the air traffic in Europe. And we've written close to 100 pages on guidelines that we believe will make or provide a first step towards making neural networks safe for safety-critical use. We will release a summary or a white paper of this early next year. And for anyone that's interested in sort of applying machine learning in a more rigorous manner, and this can totally be outside of aviation, I would recommend taking a look at it because I speak for ourselves, but we've learned a lot about building machine learning models more generally in better and more robust ways by following some of the things that we now demand from people building safety-critical applications. And this is my last slide. So we are based in Zurich, as I mentioned. We are around 30 people right now, started 3 years ago. I'm not sure if I'm allowed to say that, but we are hiring. So if anyone finds this interesting, please get in touch. And if you have any questions or want to talk later, just let me know. Thank you.